gas explosion. This chapter is again gas explosion. So we start to cover already and talk about the definition of the gas explosion. Yesterday, Chu Bong-shik pointed out the one mistake I made in the shock wave profile. So if I make, anybody can make mistake. If I make mistake, I want you to really point out, then we can make a corrections, okay? So can you see this clearly? Dr. Kim, can you see? So what we talked yesterday briefly, this I'm going to come back on, of course, early November when you deal with the really shock wave. But for the time being, this is what I straight up and down. And this is what I mentioned. Then I gave you equation set saying that, saying this is a P max, and this is equal to P max e to the minus T over theta, or I said this could be the whole thing could be minus maybe something like alpha T. Right, that's what I said. Bong-shik pointed out after class. He could stop, he could tell me right at the moments, then I can correct right away. What's the mistake here? In the class, we can talk anything. I always mention. There's no such a thing, you're right, I'm wrong. In the class, we discuss it and understand the things and move on. So here, I made a mistake. Sung-tae, what's the mistake I made here? I will say this is a time T1. Of course, this is a 0. Typical shock wave pressure profile, yes. The mistake is to fit in this particular the equation. I have to set this axis as a P, and this point I have to set that as a 0, right? Makes sense? And for example, I have core of explosion explosion occurs right here. I'm standing right there. Then shock wave, of course, will propagate, then hit right there. Then it's passed. Shock wave will pass by. So this is the shock wave pressure I feel right on that side here. But if I set this point as a starting point, reference point, okay, this is right there. Then I have to move this axis to here rather than here, right? So it takes a time, of course, to get the shock wave reach from here to here. Let's say time T1. This is time T1, right? If I'm going to set the reference point right here, then what do you have to modify in this equation set here? You replace T by T minus T1, right? Say yes, yes. So if you replace it, then you can start to count from the origin. This is origin, this is 0, absolute 0 point. Makes sense, right? So to use equation set to calculate the responses and all that, of course, if you use t minus t1, that's okay, but your reference point is right here. And the same thing happened for the air explosion problem set. Could it be down there? But this is P max. So I said this point is over pressure. This is under pressure. So equation set here could it be PT is equal to P max e to the minus T1, I use a T plus, right? I use a T plus. This point, this is a T1. So this is T1. This is gonna be T plus. I use this, and or again, this I can use alpha t, and then 1 minus t over t plus. You have to replace the same thing, right? If you're going to shift this guy to here, right? If you're going to shift that to there, then to down here, this is set as a 0, then this is the equation set. But if you're going to use this point as a reference point, then you have to move t to t minus t1. This is where. In other words, sometimes there is a convenience for the computation. So, for example, I have a ship. Explosion occurs right there. Then when it explodes, the shock wave will propagate and hit the surface of the hull. And my interest is not the shock wave propagation in the ocean. My interest is what happened after it hit the target. What happened after the shock wave hit the platform. That's my interest. Then I don't care from here to here. It takes a time up to T1, which is R over C. This distance could be R, right? Which is the so-called standoff distance. Standoff distance is the distance between the explosive or source, some people call, to the target, right? Direct, right? So some people start to counting the time right from here. Then this equation set is all okay, but oceanograph who work on that area, my interest is not only here but also here. Then reference point is here. When it explodes, then you start to count, right? When you start to count, then it's the reference time 0. Then you have to replace t by t minus t1. But another aspect, so over here, over here, I'm going to call this guy, has a specific name. This is a dynamic pressure. Some people call the gauge pressure. This kind, same thing down here, dynamic pressure. But when you're dealing with pressure gauge out there, for example, this is ocean. So when you put it down the hydrophone here with a certain depths D, there is a what? There's an initial pressure, right? Initial static pressure. It's hydrostatic pressure. Initial hydrostatic pressure. Rho GH, rho GD. So you can, if I draw the shock pressure in an absolute sense, I'm going to draw this guy now as a P. This is absolute, nothing to confuse here, absolute pressure. Okay, I'm going to draw the absolute pressure. So right at the point here, your charge could be right here, or source could be right there. I have to draw the initial pressure. Initial pressure is there when you deal with the total pressure. Confusing? Nothing to confuse. Total pressure. My interest is the total pressure, which is absolute pressure at the time here, which initially everything is all calm, no gas explosions, no chemical explosions. Then I have, what pressure do you have? What pressure do you have? You have hydrostatic pressure, right? That's it, right? Sure. That's all?
Yes.
Is it yes? Or no? Or more? Where the atmospheric pressure going? Do we have a pressure right now? Are we under pressure? What pressure? Gravitational pressure, right? We are under atmospheric pressure. We are not in the vacuum. Right? So we are in what? 1 bar? Right? 1 bar. Or 1 bar. 1 bar is how many megapascal? Anybody knows?
1 bar is 101.3 kilopascal.
Yeah. See? 1 point?
101.
101 kilopascal. 101 kilopascal is 1 bar. That's what Hyun-Chul said. 101. We are under 101 kilopascal. Gosh, that's amazing, isn't it? In gravitational unit, 1 bar is 14.7, 14.3, I think. Not 14.3 psi. Pound per square inches. Typical is 1 bar. 101 kilopascal. Plus hydrostatic pressure. So you have this guy is initially you have PA plus rho GD. This D is the hydrophone depth. For example, just example. In other words, simply static pressure is there when you deal with absolute pressure. But usually for dynamic analysis, you don't have to worry about the static pressure. Why? When you compute the response for moving loading, dynamic loading, of course, we don't care about the static pressure is there. You can just compute the response, which is a static response. You can simply add on to it. Right, Songtae? So nothing changed. Then you can add over here. It could be up. Then what happened? Is it going down in the same downhill like this? No, because there is always the static pressure in there. Then this could approach to the static pressure, which happened to be the atmospheric plus in this case is hydrophone, the hydrostatic pressure. But if some other things happen, of course, it could go, a lot of things could happen, things like that. We'll discuss all the aspects starting November. Because I'm really doing my best to say some meaningful things on gas explosion. And you will, of course, you're not going to just sit there listening. You're going to work on gas explosion, doing some good initial research on gas explosion yourself, in addition to the fire. I want to assign the gas explosion good assignment to replace you called exam. On the gas explosion, toward end of October, then you can work on the month of November. Then we'll working on November. We're gonna work on the underwater explosion stuff. Okay, so same thing happened. You could have initial pressure goes nowhere, go up and down. Okay. So this is what the Bongshik, he came late. Bongshik. So this is what he mentioned to me. It's very clear. Gas explosion. How many of you read chapter 1? How many feels who cares? You should care. Whoever just sitting in for fun, that's okay. But listening is also good. And but whoever working on the Professor Chang's lab, you should, I said should, not you may. You should read Gas Explosion Handbook. It will provide you an excellent foundation to work on the gas explosion, the areas, in conjunction with other chemical process design or structure system design, the vice versa. And this highlights, I did it just to point out some importance. I talked about that before. And also Blavis. You called this is a Blavi, is it correct? I called the Blavis. This Blavis, when you think about the Blavis, then you have to talk about the pressure vessel. And you are talking about high temperature. So then this could generate something like a domino effect. Then you can think of the high pressure vessel connected by the like a train, and it's like a continuation of connecting the pressure vessel type. And deflagrations and detonation, we talk a little bit the Monday. Deflagration mode of the flame propagation is subsonic. So read well between the line. The deflagration propagates at the subsonic speed relative to the unburned gas. Unburned gas is there. It's moving also the faster. And I think it's on the other chapter or a later portion of this chapter. I think should have a nice 1D picture. We're going to wait until that time. But this speed is at 1 to 1,000 millisecond. Depend on the unburned the material property. Could it be oil? For the oil, acoustic speed in the oil may be different, of course, from acoustic speed of the waters, air, of course, and all that. Look at the range of the speed here. Deflagration flame speed is 1 to 1,000 meters per second. Think about the range. It's a tremendous range. For the medium I'm dealing always is water. Water or air. Acoustic speed is rather fixed. 350 meters per second. 1,500 meters per second fixed. But in the gas explosion, tremendous range. Deflagration frame speed, you can deal with 1 meter per second to 1,000 meters per second. Deflagration, it simply means rapid burning. That's about all, rapid burning. Okay. And when you talk about the detonation speed here, detonation speed is supersonic, which means it's higher than the acoustic speed of the unburned gas, unburned material, whatever the material is supersonic, higher than acoustic speed in that nature. So in the fuel air cloud, detonation wave will propagate at the rate of 1,500 to 2,000 meters per second, which is pretty generous. Detonation speed in the water for the chemical explosion is 8,000 meters per second. So for the gas explosion, its range is about, it said 15 to 2,000 meters per second, which is pretty low, I can say. And peak pressure, detonation situation, peak pressure is rather low. It's a 15 to 20 bar. 15 to 20 bar. Okay. For the chemical explosion, I'm talking about in terms of the about 50,000 times the atmospheric pressure. Tremendous. It's absolute, really really absolute heat, 50,000 times the 50,000 bars. So comparison is not there. But gas explosion, every day it happened. Did you see the news last night or even this morning? Did you see news? There was explosion here in Korea. And also in China, yesterday, there was a liquid gas explosion in the large truck who carries the tank, big tank. It's not the Breivik kind, it's like liquid. You call the liquid natural, not the natural gas, not LNG type. It's a liquid gas type, it's not heated. But before the truck goes in, just before it goes into the tunnel, it exploded. And every day it happened. Busan. Last night, the CCTV camera, CCTV, they happened to see the situation of that accident. It's a human accident. He happened to touch the valve, then that looked like loosened up or broke. Then Busan just vaporized and came out. Then spread all over. So usually explosion, especially gas explosion, is always connected to the accident. That connected to the safety. That connected to the safety management. One small mistake looks like kills everything. So this subsonic deflagration, the pressure is very, very small. It's just this several bar. G is absolute gravity. And depend on the situation, gas explosion magnitude is changing tremendously. Worst situation is gas explosion in the confined area. Confined volume is a disaster. And a lot of time there is an opening or ventilation, they put that in. Then of course, at the time of gas explosion, the induced pressure is going down pretty fast. As I mentioned the other day, we're going to conduct the explosion testing on the above the ground, but covered by the soil. April next year. But usually explosion could occur in the confined area. All the neighborship, everything is all compartmentized. When the missile hit the deck, it doesn't explode right at the deck. When it impact occurs, it penetrates down to the compartment, then explode. Then what happened? That's a confined, but still they have the ventilation openings there, but that's not sufficient. It could be a big problem. But as I see North Sea, a lot of oil drilling platforms, When I see the fire in the pictures and all that, looks like it's a confined explosion generate tremendous safety problems. This is partially confined situation. I'm passing by, but I want you to read, okay? And the consequence of a gas explosion will depend on, and summarize the following here. As you see here, there is a tremendous parameter, not just one parameter, type of the fuel. Depend on the type of the fuel, the fire ignition temperature is all different here. Seems to be methane is pretty at the low temperature. It can ignite the fire. But for hydrogen, you call hydrogen or hydrogen? Hydrogen. For the hydrogen, all over the range of the temperature, it can ignite, dangerous. So there is no such a rule, but a lot of parameters, type of the fuel. And European people, they use S rather than Z. In North America, they use Z, jet. So that doesn't make any difference. Depend on what you use, what type of the oxidizer you use is going to be different. Air is also oxidizer. Okay, a lot of different oxidizer type. Size and fuel concentration of the combustible cloud. When you say the cloud, you're talking about the gas cloud. Location of ignition point, strength of ignition source, all this you have to consider at the time of the design of the fixtures, structures, or system you are dealing with. Size, location, and type of explosion, the vent area. Venting is important as we talk. Location and size of structure element and equipments. Mitigation scheme. What's the mitigation? What's the meaning of mitigation? 공식이 mitigation이 뭐야?
사고가 발생했을 때 사고의 규모를
줄이는 거. mitigation 줄이는 거. spread 하는 거. Abdullah, you know the mitigation? The meaning of the mitigation? Mitigation is really make it lower. So mitigate the shock means somehow lower the shock, vice versa. Loss experience is when you have box lunch in the with a friend, then I want you to read all this loss experience. This is 1988, based on the 1988 report. That's already 20-some years back, but you don't have to go back to 20 years. But every day you see, maybe you can start to log in what you see every day out there. Is gas explosion experience is tremendous. But one thing clear, as you see the figure shown in next page, 42% of those accidents, including all this shown here, were caused by the vapor cloud explosion. Vapor cloud explosion is equal to the gas explosions, okay? So if you see the vapor cloud explosion, that's really same identical to gas explosion. As I look at a few different books, vapor cloud explosion, they just use their own and try to make it name, but everything, all this is gas explosion. Gas is a mixture of the fuel and the oxidizer. And the worst thing is 42% of accident is by the gas explosion. Amazing. Professor Han showed during his lecture, I remember, 42% vapor cloud explosion, gas explosion, 35% the fire. Fire and the gas explosion, you can't really separate them together. They're something like husband and wife, they always go each other. They love each other. Whenever explosion occurs, there is a fire. Regardless, always work together. And this is other type of the explosion. Okay, and the black area is said is a wind. So maybe wind-induced explosion type is what you can see. And did you read this a little bit or not? Say something. I don't want to keep talking myself. Yes, sir, did you read? Not yet, right? Okay. 동식, not yet. Huh? When you going to read? 성태, you are willing to read? Don't say no. Yes, right? For your own sake. 정호, you will surely read. You read already.
Yeah, I just.
You are the expert all this. But read this, you already made a copy.
Yes.
So.
I made the copy from the web page, screen capture.
And at the same time, you can learn the English. This is very straightforward. The English, the phrase is here. So very easy to read. And Hyunchul has made a copy. So if you make a copy, each chapter at a time, then by the time you finish, you can have a whole handbook. And Flixborough accident. This is England. I added the England here. All this accident, you can investigate. You don't need to travel. Everything is where? Where is all the information you can access? Where? Internet. I access internet. Everything, all the detail is there. What else do you need? So you have explosion of information. When I was in your era, age of 30, no information available. Spend the whole day, whole week in the library, still no good because it's old information. But now, everything is on your hand. So luxurious. So Flixborough accident, this much the information is, I feel, is more than enough. So this is something like 28 people killed. That's a large number. And as you as you see here. Always at the end of the paragraph, there is a lesson learned. That lesson learned is very important. So all this accident as it described, then lastly it shows what lesson do I get. So lesson learned. We can learn if the inventory had been smaller, the flammable gas cloud would have been smaller. So reduce inventory, which looks like nothing, but it's not true. All the days, each company has a huge warehouse and have a stocks of the merchandise to ship out. No more, right? You know that. You heard about that, right? For example, I heard Nike is, they have nowadays their business may be spread out much more. They deal with shoes, sneakers, all kind of the things, right? And of course, there's sports jacket, even cap, you name it. Do they have a huge warehouse sitting next to their office? They don't have a warehouse. Do you know where that? They don't have any single warehouse. Everything is right on the spot, the factory, manufacturing places and all that. And same thing happened to Amazon.com. I buy the book. I bought not only book, lots of other stuff. Sometimes cameras, I bought it from them. Then when I order it, it come within 3 days. Here, book, 3 days it came right in. And I found out that they have a distribution center, maybe even in Korea someplace, nearby. They ship out from right there. Nike ship out right near the point they ship out, then customer can get very next day. That's what happened. Inventory you don't maintain. I don't talk about the inventory, but it's very interesting. Reduce the inventory and control of the plant processing, process modification is also important. And of course, the blast resistance compartment rooms. Who design? You design. That's what. To design the system, you have to know the loading. I talked before. I usually repeat the same thing 3 or 4 times, then you will end up knowing how important that is. Blast resistance design, including tunnels. Tunnels, we have in Korea, everything is all small hills, mountains. When I ride a train from here to Seoul to Busan, I don't know how many tunnels I'm passing by. Tunnels after tunnels and tunnels. And when explosion occurs by accident, what happened? I know our tunnel in Korea is safe. Question is it always safe? In US, they really study hard in defense people to really check out the safety, structural safety of the tunnel. And Sweden, hydrogen explosion is always very detrimental. One case here is right in the open street of Stockholm, that's Sweden, explosion occurs. So the problem is gas explosion occurs anywhere. That's a problem. It's not happen in the remote area. No, right at the downtown of a large city, the explosion occurs. Not by terrorists, by the piping failures, pressure vessel happened to be sit there. And as I drive down Kim Hae there, right next to the highway, 고속도로, I see the nuclear reactor. I saw the nuclear reactor. I'm not sure whether it's alive or dead. See the reactor there. Right, that's right at the middle of the town. It's dangerous. In the peacetime, nobody cares. But Norway, they have lots of cases, and all this lesson learned, I want you to please read this lesson learned. Even ice cream factory. And very interesting situations here. And some are this Burj Istra or Burge Istra. This happened. I'll just talk this as a comment. Liberia, Burge Istra. This is a carrier, oil or carrier, and the two vessels sunk. But the second vessel just disappeared from the horizon. Nobody knows what happened to that vessel. What happened is right at the bottom, and by the gas explosion, just the bottom opened up. And there is no such a thing, stay time on the floating. Everything just to go down like a Cheonan naval ship. Cheonan naval ship, not bad. It floats a little bit. But this Burge Istra just opened up by the explosion, sunk right there. First or second, it happened. And this is a design matters, but here is a lesson learned and all that. More and more and more. So please read. And the last section is analysis and management of gas explosion safety. Biggest issue is safety management. So safety management is always talk, but you have to get involved to really see it. Before you get involved, everybody feel, including myself, it's going to be okay. I'll be okay. Well, there is a thunderstorm coming in. I'll be okay. Chances to kill this 1 out of million. I'm not going to be 1 out of million. What happened? 2 Korean young people who hit by the thunder, right? And they killed in Sri Lanka. 2 died. So, management for safety aspect. My plant gonna be okay. My FPSO gonna be okay. My oil drilling platform gonna be okay. No, you have to really consider. So chapter 1, I'm gonna just do like this. Then lastly, this chapter 1 insisting you have to conduct the risk analysis. I know Professor Zhang offers risk analysis, right? risk analysis course? Yes or no? Yes, right? Yes, sir? Oh, he offers, right? Processing aspect, 현철. Take 했어?
No.
Risk analysis you should. These are all probabilistic matter. So gas explosion, as I mentioned, probabilistic aspect is so important. I want you to take the course as you are in school. When you are out, done, okay? Then don't say, Professor Shin, Professor Chang, I want to come back and stay here. Then study more. That's what I heard from my students who graduated. I want to come back. This is the best environment. And school, beautiful. But when they were here, they said, I hate you because you assign too many problems, you know. But that's what the reality is. Okay, so chapter 1 finished. I want you to read, and from next week, not next week, the Friday, we'll move on a little bit faster. Okay? It's your time to read, would you? For me, it's hard to really pick and talk for all the material here, which is main thrust is reading. Okay, have a good day.